Welcome everyone. This work is entitled, Superficial Infiltration of Metal Filler over Ceramic Porous Surfaces to Production of Metal, Ceramic Joining. Abstract. In this work, porous ceramic compacts were produced by commercial aluminum oxide powders through conventional sintering route. Aluminum oxide compacts were joined to commercial titanium alloy by brazing process at 1150 degrees Celsius for 10, 20 and 30 minutes. Introduction. Dissimilar joints of ceramic and metal are employed in the feed-throughs of bionic devices. Size for hermetic bionic implants is now around $25 billion globally. Pacemakers that are used to control heart problems have a feed-through between the lead and the electronic components. A gold filler is used to bond a titanium ring to aluminum oxide in the feed-through. Different techniques can be used to join ceramic and metal, including mechanical joining, direct joining, or indirect joining. Brazing is the most noble method for joining dissimilar systems. Because the physical, chemical, and mechanical properties of ceramic and metal materials do not alter after brazing process. Brazing has been defined by the American Welding Society as a joining process that takes place above 450 degrees Celsius using filler metals or alloys, which flows by capillary forces and whose melting temperature is lower than the solidus temperature of the base metals or alloys should adhere to the surface of the base materials. Experimental procedures. The raw materials utilized were commercial aluminum oxide powder that has been used to produce ceramic compacts, high-purity commercial titanium alloy 99.7%, and metal sheet whose composed of nickel chromium iron silicon boron. This filler alloy corresponds to the MBF15 series family. Generic-grade aluminum oxide powder was selected to be sintered by the conventional sintering route. The aluminum oxide powders were pressed at 15 megapascals by uniaxial pressing. After that, the aluminum oxide green compacts were sintered at 1500 degrees Celsius for 2 hours. To make the joints by brazing, the following steps were taken. First, the surfaces of the titanium and aluminum oxide compacts were roughened by silicon carbide sandpaper. The materials were cleaned for 5 minutes in an ultrasonic tub with ethyl alcohol. Finally, the pieces were assembled in a sandwich-type arrangement, aluminum oxide plus filler metal plus T. The assembly carried out inside a graphite die. The joints were carried out at 1150 Celsius degree for dwelling times of 10, 20 and 30 minutes into an AR atmosphere. Transverse sections of the joined samples were prepared to obtain mirror-like surfaces in order to be analyzed in scanning electron microscope. Results. The ceramic compacts were made from generic alumina powders with a platelets morphology. These compacts reached a mean relative density of 61%, indicating a high degree of porosity. The joints in the 3 different times were achieved. However, as the bonding time increases, the continuity of the interface bonding decreases. Scanning electron microscope image shows the joint of aluminum oxide and titanium. The formation of an interface is shown in the cross-sectional micrograph. Chemical analysis with PMASEM at the bonding interface. According to the results, point 1 is associated with the short aluminum oxide fibers that are dispersed in the metallic matrix. The white phase corresponds to point 2 and is mainly composed of titanium and nickel, with a smaller proportion. The phase with a gray color in point 3 has a high titanium content. The remaining elements at both points correspond to the MBF15 filler alloy that diffused during the brazing process. The presence of elongated grains of oxide aluminum surrounded by a metallic matrix was observed through elemental mapping using scanning electron microscope. When the MBF15 filler alloy reached the liquid state during the joining process, it infiltrated between the pores of the ceramic. In addition, this phenomenon may have stimulated the participation of titanium as an active element. The formation of the metallic matrix of the interface was aided by the filler alloy elements, nickel, chromium, and silicon. Conclusions. The joint was made with ceramic compacts that have a relative density of 61%. Joints at 1150 degrees were possible at different joint times. After 20 minutes of brazing process, the interface's uniformity is lost. Scanning electron microscopic analysis is shown by the presence of aluminum oxide particles as reinforcing particles at the interface joint formed. This phenomenon has been attributed to a capillary force. The titanium from the base metal diffuses through the formed liquid and achieve integrating into the interface to form the metal matrix. Thanks for your attention.